So that being said, we've missed everything until right now. So yeah, thank you for being here. Otherwise, there is no way for me to for you to retrieve that. Okay, so now we are recording our lecture from here on. So we are talking about a difference equation, and you can implement this difference equation using a for loop. And then for this difference equation, I hope that by now it becomes clear that the system function is a bz divided by az, and both of them are polynomials of z inverse. And using factorization, you can express the bottom part, the top part into this, okay, into this. And so here at the bottom, we have 1 minus zp comma k, okay, k being the index right here for taking the product. And P stands for pole, while Z, this 0 stands for basically 0, okay? P is the pole, Z. So these things here, ZP1, ZP2, ZP3, and so on, they are the poles. And Z0, 1, Z0, 2, 0, Z0, 1, 0, so these are where the zeros are located, okay? So this is actually the same expression is in my video. Okay, so please refer to the video and find it. This is important. Okay, generally, I claim, at least last year on the Blackboard, I claimed that this factorization can always be done, but with one exception. Now, after considering the question you pointed out, some of you were wondering what does it mean for a pole to be or a 0 to be located at infinity. So that's a question that's raised by some of you. And this is a good question I want to address. So I've realized, just this morning, I realized that this factorization can be done only if we assume B0, the leading factor, the leading first factor here, only if we assume B0 is not 0. So if B0 is 0, then we cannot do this. Okay, we cannot pull 0 out, right? So that's one kind of important exception that has something to do with the question whether a polar 0 can be located at infinity. Okay, so why do I say that? So let's say this can be done unless B0 is 0. Okay, so what if we do have the expression, the exception that B0, the leading coefficients here, is 0. If that happens, then without loss of generality, okay, without loss of generality, let's assume that B1, at least B1 is non-zero. Okay, if B1 is non-zero, then what we can do is to consider factorizing out, or we can take out, move outside the parenthesis here is B1Z inverse. We have a B1Z inverse here, but then everything else is still the same. Okay, the bottom part can always be factorized. And the top part, if the leading coefficient is 0, we can find out the first non-zero coefficient. Right? Suppose that is, assume that is B1. Okay, if without loss of generality, assuming that B1 is non-zero, then this factorization can still be done. But now outside here, what we have is instead of B0 here, we have B1 times the inverse right here. Okay, and this is where the problem occurs. Okay, whenever this is exactly why the problem occurs. So let me ask the question now. The entire system function, has two parts. One is B1 Z inverse. The other part is what we are the kind of the formal, the classical expression, the canonical 典型的一种 expression. Okay, we know that the second part, at least also in my lecture, I suggest that you can always try to do a polynomial division, long division, and there's going to be the quotient part, the 商式 quotient, 商式 plus this is divider, that's remainder, right? 除式跟余式 or remainder, R stand for remainder, A stand for AZ is AFZ, right? And yeah, so you can always do that. And I also mentioned this part corresponds to an FIR part of the imposer song, whereas this part, when you take the inverse Z transform, it corresponds to a infinitely lasting, a right-handed infinitely lasting IRR response. Okay, so that's kind of the general behavior. But now let me ask a question: if the leading coefficient is 0, then we have a corresponding term B1Z inverse coming up right here. Okay, and what does that mean? Okay, the question then becomes, do we say that due to the presence due to B1Z inverse, do we have, what do we have? Do we have a, can we say that we have a pole at 0 or a 0 at infinity? That's the question. That's the question. This B1Z inverse part, is this, does that imply we have a pole at 0 or a 0 at infinity, or both are wrong? Okay, as the results are coming out, okay, the results are coming out. So it seems that most people agree that, actually including myself. Okay, thank you for all of you that casted the vote. I appreciate that. And so, yes, most of people said agree that both are correct. But we do have some other responses. First, there are a few people saying that A, we should call it a pole at 0, okay? And interestingly, nobody says to B, and some people think both are wrong, okay? So, all right, so actually, I'm not going to suggest that any option is absolutely the most correct thing to call it. My actual answer, okay, to this question is, this is not important. It is not important to call. So actually both make sense, okay? We can call this a, so maybe the reason why you might be able to call this a pole at 0 is because, let's say B1, let's just consider B1Z inverse, okay? B1Z inverse. B1Z inverse, of course, is B1 divided by Z, and there is a pole at 0, okay? But also, you can say B1Z inverse is, so that leads to the interpretation, a pole at 0. But on the other hand, you can also say, hey, this B1Z inverse thing here, if we think of any Z, actually this is not even a good expression, any Z such that any Z equals to R times EJ theta, okay? And we let R approach infinity, meaning that if you move Z infinitely far away from the origin, okay? If we move Z infinitely far away from the origin, Z minus Z to the inverse is gonna approach 0, right? And this is at the top part, at the what? Numerator part, 在分子, 在分子. So that means that we do have, you can see that when Z approaches infinity, infinitely far away, then our numerator becomes 0s. So you can, in this sense, you can say that infinity is the root of this polynomial, of this function, okay? Because it causes this function to approach 0. So in that sense, you can say, also say that this is a 0 located at, this is not even a good expression, okay? The more rigorous way to say it is that Z has a distance to the origin, it has an angle. And if we let the radius approaches infinity, that's what it meant. So yeah, but people say this. People sometimes say that we have a 0 at infinity, and they say it like so smoothly. We should not call it wrong. Okay, so that's why my answer says that both are correct. Okay, you cannot call that they are wrong. Okay, but this is not the point. Is that this is not the important point. As far as we focus on solving the impulse response, that's what I think. What is important here still is the issue. The main task is not to argue where we have a pole 0, but to solve the impulse response. That's the most important thing. Okay, so this is not an important issue. This pole 0 issue is not important as far as the impulse response is concerned. So that's my conclusion. Okay, and so this is actually very simple. So that leads us back to what this term, the physical meaning part, because you're asking the physical meaning of having a pole at 0, 0 at infinity. What does that mean? The meaning is actually fairly simple. the meaning, because that's the source of the problem. Okay, and this term, remember that this term is fairly easy in that Z inverse just corresponds to one sample of delay. No, one sample of delay. So when you calculate the impulse response, here's what you can do. Okay, you can first calculate the impulse response of this part. As I just mentioned, it has an FIR part and IR part. Okay, and after that, you delay everything by one sample and multiply by this factor. So that's what it means to have a zero at infinity or a pole at zero, simply a delay, one sample of delay. And that makes a lot of sense because this can only happen when the leading, remember that this problem only occurs when the leading coefficient is zero, right? And what does that mean? What does that mean for the leading coefficient to be zero? That means that we have yn, the linear combination on the left. On the right, that means the xn coefficient, the corresponding coefficient for x of n is zero right here. So that means that the input is not going to affect the output until later. Though that's one sample of delay. Okay, so that's what I want to share with you. I'd like to pause a bit. Any question? I hope you like this interpretation. Okay, so really the discussion of whether or not we have a pole at zero or zero at infinity, that's not really important. What is important is that it just corresponds to a few samples of delay. And in this case, we assume that B1 is the first non-zero coefficient. So we can just calculate the impulse response as if shifted by one sample, and then remember this shifting. Okay? You only need to remember shifting. Okay, good. All right, so I hope this is helpful. Thank you very much for raising this question. I feel that I also learned something, okay? But let's still move on to our final part. There are two questions. One is regarding homework number 4. Homework number 4, okay? And the second is, why is the group delay, why do we define group delay like that? So let me answer this first, because homework number 4 is also related to group delay, okay? So let's try to talk about group delay. So the group delay of a system, whether it's continuous time or discrete time, is similar. We define the group delay as a function of frequency, and is defined as the negative of the argument of our any given system, the phase response, the first derivative of phase with respect to frequency, okay? And that's group delay. And the question is, why do we define it like that? So by now, I hope that you have seen some plots. They can, if this is the phase accumulation, the phase of a system, okay, omega can go from 0 to pi, right? So assuming that, yeah, that's the range of omega. Okay, so we are looking at the slope simply. So we are suggesting that you calculate the slope right here, and that slope corresponds to a latency, a delay. Okay, but then the question, that's a very good question. Why do we look at it? This is strange, right? Looking at the slope of the phase response. Well, what could that really mean? Okay, so to answer that, I can point you to, let me first point you to a exercise, okay? An exercise is a textbook. So there is an exercise in this chapter 5 that actually deals explicitly with a particular example of group delay. Yeah, this is the question, 5.63. Okay, if you're interested, please take a look. So in this question, I'm just going to follow. This question assumes that we have a system, that we have a few systems. First of all, a system with constant phase. Okay, that's one system, very fairly simple system. And the kind of a second step into making it more slightly more complex is that for the system to have a constant slope. persistence phase response to have a constant slope. Okay, and so in this particular example, when the system has a constant phase response of constant slope, and now we make an assumption. Okay, what's the physical meaning? What's the meaning of group delay? A group delay applies to a narrow band signal. That's one important thing to point out to begin with, an important concept. So now if you consider a signal which is to modulate a narrow band signal by a carrier, if you will, in terms of communication, the carrier of frequency omega 0. Okay. So if we have a signal like that, then its Fourier transform, we know that modulation to multiply by a carrier is to shift the spectrum to the right, right? So what we have here in the frequency domain is going to be a narrow band signal. Okay, this is the kind of the magnitude spectrum we are plotting. The magnitude spectrum is going to be centered around frequency omega 0 with a bandwidth that is much narrower than the center frequency. That's the assumption. Okay, let's assume that our signal follows this property. It's a narrow band signal, a low pass narrow band signal filtered by, no, not filtered, but modulated frequency shifting to omega 0. Okay, so if we have that kind of a signal, it turns out that if you work out the homework, you can show that the output, remember still we have a system, okay? We have a system and then the input is a narrow banded signal and the output, let's still call it y of n. It turns out that this is exactly the meaning of a group delay, and also another term is phase delay, okay, phase delay. So it turns out that your output will have this expression, exact expression of the S part. The narrowband part is going to be delayed by so much. And the carrier, okay, the carrier part is still have this, still have the same frequency, but the phase is shifted, okay? Yeah, but so really the group delay is the delay of the packet. So my conclusion is that the group delay is the delay of the packet. So 那个封包的 delay, what do I mean? So let me just get back to my writing pad. So let's get back to this discussion. This is really important. Thank you for raising the question. So the issue is that when we want to understand group delay, when we want to go that group delay is a function of frequency, okay? So let's say at any particular frequency omega 0, the group delay is this, and considering omega at omega 0, that's a group delay. Group delay is a function of frequency for the system. It means that if we have the system H, and we are going to send an input signal, which is a wave packet, okay, modulated by a underlying fine structure is the carrier. And this carrier is cosine omega 0 n, okay? And the envelope here is pretty smooth. That means it's low pass. It's a narrow band signal. Is that all right? So I'm saying that this envelope signal is a narrow band signal that carries the information, that actually contains some information that you can try to modulate. Yeah. And then we send its frequency to a higher frequency by multiplying this wave packet with the cosine function. Okay. So let's call this the input, and the system produces an output. It turns out that the output, in the output, this wave packet is going to occur elsewhere in time. It can be delayed, let's say, if originally it's centered around time n0, okay? And time, let's say time n0 is right here. And after going through the system, the system can incur a delay. So now the packet is moved to the right, and this is n, okay? Packet is moved to the right, but the envelope is gonna pretty much preserve the same shape, but only moving to the right with possibly also a gain, okay? So if this is unit height, then the gain should be the magnitude response at that frequency, okay? So that gain, this height right here, should be in accordance to the magnitude response at the frequency of the carrier. But then this delay is the group delay. That's what group delay means. Okay, any slowly varying signal modulated by a high frequency at that carrier frequency, when this packet goes through the system, it's going to experience, it's going to experience a delay of so much. And this thing doesn't even have to be an integer, by the way. It does not, in general, it can be any real number. It can also be negative, okay? Meaning that sometimes when the signal goes through a system, this is strange. This is actually pretty strange. That the group delay can also be negative. Group delay at certain frequencies can be negative. And that does not violate the causality. Okay, so that's a separate issue, okay? But they mentioned that group delay, that's the meaning of group delay, considering a wave packet, okay? And that's in the homework number 563. If you are interested, please take a look. All right? Any comment? Is it good? Slido 上面有新增问题。The TA is telling us we're gonna run out of time pretty soon. But okay, so anyway, so that's yeah. So please consider this picture. This is an important picture. I want you to make it clear. Also, in my lecture, in the textbook, there is an example of calculating group delay, and some of them sometimes can be negative, sometimes it can be positive. But an important part for all of us to at least keep in mind is that for an all-pass system, the group delay is always positive. Okay, the group delay for any such packet is always moving to the right. Okay, that's an important property of an all-pass filter. And we're gonna, in my video, we can approach that, we can prove it by geometric interpretation on the unit circle. So remember that in the video, at one point I was drawing, where's my, sometimes I cannot find I have too many windows. Here, this one. Okay, yeah. So remember that at one point in the lecture, I was considering an all-pass filter with pole inside, zero outside. I was considering this angle, right? Something like that. I was considering that when we go or move around the unit circle, that this angle is always going to be going more and more negative. Going more and more negative, okay? So, but that's in this homework number 4, which you just finished, I propose to work on it using a different approach, using bilinear transformations. Okay? So I'm gonna maybe quickly go through that. And we can come back to this anytime, okay? By the way, this bilinear transformation, so in this question, we are going to move from the discrete time domain to the continuous time domain. And this is a classical transformation that we will come back to, okay? When we come back to IR filter design, we still come back to this this method. But here is kind of a preview. This transformation is called bilinear transformation, and it's a mapping from Z domain to the S Laplace domain. Okay, from Z to Laplace domain. So the A part, you should be able to show that the transformation maps the unit circle to the y-axis. Okay, so that's the first part. The first part, I want you to prove that this bilinear transformation by specifying S and without a loss of generality, let's assume that we don't worry about the normalization factor for now. S and Z, S is a function of Z. Okay, S is a function of Z. And it turns out that you can show that if Z is on the unit circle, if Z is on the unit circle, the corresponding S is on the y-axis. This is S domain, that's a Z domain. And this is a transformation mapping from Z to S. Okay, so the unit circle, if you go counterclockwise, it turns out that the corresponding S is on the y-axis moving upward. Okay, and if you know your complex analysis well enough, you know that this function is analytic everywhere except at Z equals to -1. There is a singularity. There is a pole, basically. Okay, that's where we have a pole. Actually, in this, I'm going to say Z plus 1, Z minus 1. Okay, so we have a pole at a singularity. A pole is a singularity of the system function, right? So that's one thing. But otherwise, then part B, I ask you to find the expression for the inverse transform. Z can also be expressed in terms of S, and the answer is Z is fairly simple enough. Hopefully, Z, let me refer to the answer that the TA has prepared for me. Z is going to be 1 minus S plus 1 divide 1 plus S. Okay, so that's that's an inverse function, right? So if the inverse function exists, then of course it's 1-to-1. We have just explicitly derived the inverse function. That's the inverse function. So it's in other words, we found out that this function is 1-to-1. Okay, 1-to-1. So no two different points at Z domain would be mapped to the same point at S domain. That's what we mean 1-to-1. But then the question is whether or not it's onto. Where does the mapping onto? Does it cover the entire space of S? The answer, unfortunately, almost yes, but no, because here, it turns out that no finite Z is going to be mapped to S equals to 1. So there's an exception, okay? There's an exception. S only approaches 1 when Z moves far away from the origin. So there's the answer is almost yes. This question, the answer is that this function is 1-to-1, but not onto, because of its range does not contain S equals to 1. Okay, but otherwise the entire S plane is covered. And I was gonna point out that if you are familiar enough with your complex analysis, the function of a complex variable, this is going to be a conformal mapping. This is a conformal mapping, and it maps. Imagine that if you're going around the unit circle, counterclockwise, a conformal mapping tells us that what's on the left-hand side, which is inside the unit circle, remains on the left-hand side after the mapping. So the inside maps to the left half plane, and the outside, if you imagine that you're going around this unit circle counterclockwise, so the outside remains on your right hand, right? Outside, can we agree that the outside remains on our right hand? If you imagine you're going counterclockwise, okay? And the outside, the right hand side maps to the right hand side. So the right half, so the outside of unit circles maps to the right half plane in the S domain, okay? All right, so with that, so the question is, then I want you to show that now we have, let's jump to E part, Let's say now we begin with a system function, an all-pass filter. Where A can be complex valued, okay? So now we know that in this system, I'm going to plug in Z is a function of S. That's an inverse bilinear transform. Then we can define a corresponding continuous time system, which has a system function that is defined as H to the Z of S. Then it becomes a function of S. And then what does that mean? What does that mean? Okay, so if you will just to kind of keep track of everything, and you'll reach that this system function in the Laplace domain also is a ratio of two polynomials of S. Okay, two polynomials of S, and you just with some effort you can figure out it's 1 minus A conjugate. And I forgot, I think the TA when TA is preparing me for it should be A plus, okay, something like that. With some effort, you can figure that out. Just need to be super careful. So now you just plug in Z equals to Z of S, and that's the corresponding continuous time system, okay? But then I will share with you that when you are doing this this substitution, 代入的时候, this substitution, what happens is that in general, a 0 in the Z domain is going to be mapped to a 0. It will correspond to a 0 in the S domain. And the pole is going to correspond to a pole. Then it becomes important that this is, for all path system, we have a pole inside and a 0 outside. And as I just mentioned, after the bilinear transformation, we have the corresponding continuous time system whose Laplace transform, Laplace system function, is going to have a pole somewhere and 0 somewhere due to the presence of pole and 0 in the Z domain. And as I just mentioned, the inside of the unit circle is mapped to the left-hand side. So we have you can expect a pole somewhere to the left of the imaginary axis. Whereas we have a 0 somewhere on the right of the imaginary axis. And it turns out that part E, I'm asking you to show that actually they are located at image locations. If you think of the imaginary axis as a mirror, then they are actually equally distant apart, and the imaginary axis actually bisect the line. Okay, the line, if you connect this is a right angle. All right, so it turns out this is true. It turns out that this is true, and because the magnitude response, further because the magnitude response on the unit circle is a constant. This is all path system, right? So after this substitution, we should expect that the magnitude response along the y-axis. So that's what we're talking about, continuous time system. When we evaluate the Laplace transform on the y-axis, you are calculating what we are looking at is the Fourier transform. Okay, we're really running out of time. And it turns out that all paths actually is simpler to show that indeed the magnitude response of this is simpler. It's simpler to show that the magnitude response when we evaluate on the y-axis is a constant. And that simply follows because this line, wherever we go on the y-axis, this segment is going to be equally long as that segment. So when we take the complex division, the magnitude divides, and they are equal. They're equal. And we are really running out of time. And the final part is for the phase response. It turns out that the phase response, let's say we have a 1 pole here, 1, 0 right there. The phase response, that phase, it turns out to be 2 times this angle. Okay, 2 times this angle. When we move our frequency along the y-axis, it turns out to be 2 times that angle. That's a phase response. For any given omega, the phase response turns out is 2 times this angle. 2 times this angle. Let me call it this angle alpha, 2 alpha. And alpha is the function of omega. Okay, so if you will stay with me for a few more minutes. So this homework actually, this is kind of a geometric interpretation after mapping it to the S domain. After mapping to the S domain. So I'm asking you to convince yourself that now we can move our frequency upward along the y-axis. And I hope you can convince yourself that when we move that our frequency on the y-axis, then this angle becomes more and more negative. More and more negative. Can we agree on that? Can you imagine that this angle becomes minus 90 degrees and so on and so forth? It's getting more and more negative, always. So we are showing that this angle here is going more and more negative. So in other words, you will take the partial derivative of it with respect to big omega. This is going to be less than 0 for all omega, for all big omega. Okay, and it turns out that omega, this big omega and the small omega also has a relation. And we'll come back to that actually, so please do not be afraid, okay? But I'm sorry if you find this homework to be overly challenging, but it turns out that big omega and small omega are related by the tangent function. For omega between, let's say, minus pi and pi, okay? So that means that this function is monotonically increasing. Monotonically increasing. So since we just convince ourselves, the final step is that since we just convince ourselves that this derivative is always negative in the big omega domain, then we can conclude that the angle if we take the first derivative of this angle with small omega, it's also going to be always negative. And the reason why is because this derivative is going to be equal to, we can first, one way is the other. Let's apply the chain rule. The chain rule, okay? Right? And we've shown that this thing is always negative, and this thing is always positive. Therefore, this thing, that's always negative. It is always negative. And what is this? This is minus our group delay at that frequency, right? So long way by using the bilinear transform. I want to show you this is another way you can show that the group delay of the all-path system is always positive without going too much into trigonometry. Okay, this is, everything is geometric interpretation with a bit of geometry. Okay, so so hopefully this is a bit fast, but let me assure you that we'll get back to bilinear transformation when we will formally introduce it. Okay. So I hope by that time it becomes more clear what we are doing. We've been doing on homework number 4. All right. So since we are running out of time, thank you for joining us. And if you just still leave a question somewhere on YouTube, send us a note, start a discussion forum anytime, or even you can make an appointment with me myself for my office hour. And so with that, I'd like to stay online for a bit, but you can feel free to leave now. Yeah, 下课. Okay, class dismissed. Thank you.